My dear students, so far we have discussed about MOSBAUER spectroscopy till instrumentation part. What if we get a spectra from the MOSBAUER spectrometer? How we can analyze it? What information can we infer from the spectra? For that purpose, we need to understand the spectral parameters of MOSBAUER spectroscopy. And the three main spectral parameters are isomer shift or resonance line shift, quadrupole splitting, Zeeman splitting or magnetic interaction. Okay, so we will discuss in detail about these cases. First, we will brief the concept. We all know that the MOSBAUER spectroscopy, which involve the nuclear transition upon absorbing the gamma radiation by the absorber or the sample. The gamma radiations are emitted by the source, right? So, the nucleus which we have focused for this analysis, which are surrounded by many parameters, because the nucleus can be surrounded by the internal electrons, the K shell, L shell, M shell is there. So the core electrons are surrounded around the nucleus, right? So the electron has an ability to influence on this nuclear transition. That's the first parameter. The second thing, there are many magnetic field due to the presence of that electron. There's an internal magnetic field that can be generated. This internal magnetic field can also influence the nuclear transition. In addition to that, in order to study more on this spectra, externally the scientist or we will supply some external magnetic field also, right? That's a second parameter factor. And the third factor is if the nucleons are possessed in an energy levels, right? Just like electrons, which are possessed in ground state, excited state, just like that, the nucleons, protons, neutrons are possessed in certain energy levels. Upon getting a gamma radiation, they get excited, right? From ground state to excited state. So these charges are distributed in the nucleus, right? If these charge distribution, nuclear charge distribution can also influence the nuclear transition. If there is any change in this nuclear charge distribution, that can also influence this nuclear transition. So these are the three factors. And the first factor is isomer shift. Isomer shift is also called the resonance line shift. It's mainly due to the electronic interaction. The surrounding electron in a nucleus, the surrounding electron can influence the nuclear transition. As a result, isomer shift happens in the spectrum. If we are taking a spectra of a given sample, if the electron distribution is different, can cause a spectral change. See, this case, this spectra is undisturbed case. That means undisturbed. That means if the source and the sample is having same chemical environment, so the spectra we obtain is at the trough, because in the MOSBAUER spectra, the y-axis gives the absorbance in percentage, absorbance in percentage, and the x-axis is the Doppler velocity. The velocity means the MOSBAUER drive is moving towards or away from the sample, so that the source can be approaches and away from the sample to tune the energy, right? So the velocity in the x-axis and y-axis gives the absorbance in percentage. So if there is no chemical change or environment change, the spectra we will obtain 0 and the plus direction is there, minus direction is there. There is no shift, no interactions. Okay, that's an identical species. If there is isomer shift, that means if the source and the sample energy level differences is occur, what happen? The energy of the sample means the absorber is slightly different. This is the case of the first one. The first one is the case of isomer shift. As a result, there is a shift in the spectra from the central point to another in the plus direction. It can also come to the negative direction. So this is called isomer shift delta, represented by delta. If the nuclear charge distribution, we will discuss about that. The nuclear charge distribution, just like electron charge distribution, the probability to find the nuclear charge distribution is deviates can also interact the nuclear transition. As a result of that, the excited state split into two. Okay. As a result, there's a doublet happen. A doublet in the spectral lines. That cause of quadrupole splitting. EQ, which is represented as EQ, where E is the electronic charge, Q is the charge of the quadrupole moment charge. And what about this Siemens splitting? Due to the presence of, it can be due to the presence of internal electron, means the electrons are revolving around the nucleus. So the magnetic field created due to the movement of electron and this internal magnetic field, or we are applying external magnetic field. So in the presence of a magnetic field, what going to happen? The nuclear transition of both excited and the ground state split into. So the 3 by 2 which gets split into, if I is the quantum number, spin quantum number of nucleus, how many times, the number of times the energy level split, that will give 2i plus 1 levels. 2i plus 1 sub levels are forming. So 3 by 2, the 3 by 2 sub level, 3 by 2 energy level split into 4 sub level and 1 by 2 energy level split into 2 sub level. So as a result of that, we will get a sextet. So a 6 hyperfine splitting occur in the spectral line. These are the important spectral parameters we must know in order to analyze, in order to infer data from the spectra that we obtain from the MOSFET spectrometry. Now we are moving to discuss in detail about each spectral parameters. The first spectral parameter, isomer shift. So we are going to discuss in detail about isomer shift. Isomer shift, or in other term resonance line shift. We have already learned that in the spectra, this is the zero, the central point, and the positive velocity is there, velocity in the x-axis and absorbance in the y-axis, and negative velocity part is there. This velocity is the Doppler velocity, that is the movement of source either towards the sample or away from the sample. That can be done with the support of MÖSSBAUER drive. So in the spectra, the spectral line shift from the central 0 point, then we can infer that there occur an isomer shift. What is the reason? So let's consider this energy diagram. If the source energy level 3 by 2 to 1 by 2, the nuclear transition from the excited 3 by 2 to the ground level 1 by 2 creates the generation of the emission of gamma radiation, E gamma. And if there is no chemical differences, chemical change in the chemical environment between source and absorbent, both the energy level, that is E gamma, must be equal to E absorber, right? If there is no chemical change in the or chemical environment differences between source and absorber, the E gamma will be equal to E absorber. So nuclear transition happen, we will obtain spectra, and the spectra we will obtain does not have any spectral parameters that is an ideal spectra, right? If there occur an isomer shift, what is the cause of isomer shift? The energy levels of absorber or the sample get tilted or will get changed due to the difference in chemical environment. What is this chemical environment? And this chemical environment is due to the presence of the surrounding electrons. See, this is a nucleus, right? This is a nucleus, right? The nucleus is surrounded by K shell is there, K shell is there, right? K shell is there and L shell is there and so on. K, L, M, N shells are there, right? Energy shells are there. So the presence of these electrons are revolving around the nucleus. So these electrons can interact with the nucleus through Coulombic interaction, electrostatic interaction or Coulombic interaction. These electrons interact with these nucleons or nucleus. As a result of that, this will disturb the energy, the nuclear transition, the ideal nuclear transition. So as a result of that, the nuclear energy levels of the absorber get tilted and the energy gap will not be equal to the gamma radiation generated or emitted by the source nuclear. Let me repeat, the energy shift due to the difference in the electron density at the source and the sample or the absorber. There is if the electron density around the nucleus is different in both absorber and the source, there should occur an energy shift or a change in the nuclear transition energy level. As a result of that, isomer shift happen. So energy shift due to the difference in the electron density at the source and the sample is known as isomer shift or resonance line shift. And as a result, why? Because of the Coulombic interaction of electron with the nucleus. Okay, this is the concept. And what will going to happen? In that case, the energy, the gamma radiation, energy of the gamma radiation emitted by the source does not match with the energy gap of the absorber. So in that case, we will not get a spectra. So what we will going to do? We have to get that spectra, right? So we are applying the Doppler concept. We are applying the Doppler concept. When the train comes closer to us, we will listen, we will hear the sound, the horn in a louder voice, and that means the frequency will be higher. If the train moves away from us, away from the station, the frequency of the sound, the horn will decreases. Just like that, if the energy of the absorber, if the energy gap is higher than that of gamma radiation, if the emitted gamma radiation is more to compare with the energy gap, but the source will move towards the sample. The source will move towards the absorber or the sample, so that the frequency, the energy of the gamma radiation increases by a value delta E. So the energy of the absorber so as to match with the gap. So the source move towards the absorber to match the energy gap with the energy of the gamma radiation. So the actual absorber energy will be equal to E gamma plus delta E. If the if the energy gap of the absorber is smaller when compared with the emitted gamma radiation, what will going to happen? The source will move away from the absorber. As a result of that, the actual energy of the absorber or energy gap will become E gamma minus delta E. This delta E is the change in the difference, the change from the central point, right? And this is delta E, or delta is equal to delta E, and this is called chemical shift. So in order to cope up with this chemical shift, we are applying Doppler concept to match the energy of the gamma radiation with the energy gap of the absorber molecule. So due to Coulombic interaction with the surrounding electrons with the nucleus, this isomer shift happens. As a result, the energy of the gamma radiation may or may not be equal to absorber energy gap. In order to match with the energy gap, we are applying Doppler concept. The mathematical expression of isomer shift or resonance line shift is given as the 2 by 5 pi Z square into the psi square absorber minus psi square source into the square of the average radius of nucleus at excited state minus the square of the average radius at the ground state of the nucleus. So from the expression itself, it's clear that the psi square means psi is the wave function that gives the possibility to find electron around the nucleus. Psi square gives, according to quantum mechanical concept, the probability of finding an electron around the nucleus. So this part of this expression gives electronic property of the nucleus, and this gives the radius of nucleus at the excited state, radius of the nucleus at the ground state gives nuclear property. Z is the atomic number, E is the electronic charge. So this actually what exactly delta E is equal to E absorber minus E source, right? This is the expression. This delta is known as isomer shift. This simple expression is elaborated into by applying quantum mechanical concept. We obtain this result. And what exactly this mathematical expression of isomer shift give us? What information? So we all know that the probability of finding an electron around the nucleus is gives psi square. So what kind of electron? What type of electron is found around the nucleus? No doubt, it's exactly the s electron. So we all know that the nucleus, okay, around the nucleus, the probability of finding s electron is at peak, at maximum, than that of finding a p electron or d electron. Because if d electron, here is the nucleus, the probability of finding an electron, d electron around the nucleus is 0. And in the case of p electron, the probability of finding a nucleus at the center, the node portion, is 0. But the probability of finding s electron is finite and non-zero value. So the psi square of s electron is not equal to 0, is finite and non-zero value. So this psi square gives the presence of s electron density of that particular nucleus, right? So we can give the isomer shift can give information on the s electron density around the nucleus and the radial, from the radius of the nucleus also we can determine that if this is the spectra, the blue line, if 0 is the central point, if there is an isomer shift happen, what exactly happen? The spectra will move either to the positive direction or to the negative direction, right? The spectra will move either to the positive or to the negative direction. How it affect? In the case of iron, in the case of iron 57, if the psi square value increases, which means the delta also increases, the isomer shift also increases, but the shifting is more towards the negative direction. The isomer shift also higher, but in the negative direction. The reason is that in the case of iron complexes, the radius of the ground state nuclei is greater than the radius of excited state nuclei. As a result, the more negative value comes to the delta. So in the case of iron 57 MÖSSBAUER spectra or iron 57 sample, the psi square value increases, the s electron density is more, means the delta value, that shift also higher, but the shifting is more towards the negative direction. This is due to the radius of the iron nuclei at the ground level is higher than that of the excited level. In reverse of that, in the case of tin, in the case of tin 119 isotope, in the case of tin 119 MÖSSBAUER active nuclear, if the psi square value is higher, means the delta value shift more towards the positive direction. This is because the radius of the excited nucleus at the excited level is greater than the ground level. This is for your information. This is an important part. So isomer shift give details on the s electron density around the nucleus. If s electron density is less, what kind of information? If the d electron or p electron is more, it can shield the s electron, right? It can shield. The d subshell can shield. The shielding effect is more. Shielding effect is more means s electron density is lower. So if the dp subshell is there, the d electron or p electron shield the innermost s electron. As a result of that, the s electron density will be decreases, and in the case of iron 57, the shift will be more towards the positive direction. Some important points on iron 57 MÖSSBAUER spectrometer. So in the case of iron 57 MÖSSBAUER spectrometer, we have already learned that the radius of nucleus at excited state is less than radius of the nucleus at ground state. As a result, the delta value, that is the isomer shift, will be negative in negatively charged, negative value. So when the s electron density is higher, due to the negative value, delta value is also higher. But due to this difference in the excited radius and the ground state radius, the value will become negative and the isomer shift more towards the negative direction. Okay, more towards the negative direction. So, what are the important points to know? The psi square gives the probability of finding an electron around the nucleus. So, around the nucleus, the maximum probability is to find s electron. So, it gives the value of s electron density. Okay. The s electron density, if the s electron density in the source and the sample or the absorber are different, there occur shift in the MÖSSBAUER spectrometer, that's known as isomer shift. In the case of iron 57, because iron 57 MÖSSBAUER spectrometers are widely using, so we have to learn more about these iron complexes. In the case of iron complexes, iron forming Fe 2 plus 2, 6 plus complexes. So it can form D2 to D6 coordination state, right? Okay, D2 to D6 coordination sites are formed by the iron. So in the case of iron complexes, when we take MÖSSBAUER spectra of iron complexes, what exactly happens? The Fe2 plus gives a spectra at a positive direction. Fe2 plus gives a spectra at a positive direction, whereas Fe3 plus gives a spectra at a negative direction. Do you know the reason? This is because of the iron 2 plus, Fe2 plus is having D6 configuration. D6 means 1, 2, 3, 4. 1, 2, 3, 4, 5, and 6. In one case, there's a paired and the 4 others are unpaired. So D6, the number of D electron is more. In the case of Fe3 plus, unpaired electrons are there. Right? Unpaired electrons are 5 unpaired electrons, here 4 unpaired electrons. But due to the presence of higher number of D electrons, this D electron will shield the 4s electron, right? 3d6, 4s2, right? This 2, Fe2 plus, this 2 will move, and as a result of Fe2 plus is forming, these D electrons will shield the S subshell. So as a result of that, the S electron density will be decreased in the case of Fe2 plus, and due to the higher shielding effect of D electron. So the S electron density is lower, means it will shift more towards the positive directions. That's the reason why Fe2 plus gives a spectra at positive direction, whereas Fe3 plus, in the case of Fe3 plus, the one more electron, Fe3 plus D5. D5 means one more electron from this paired spin move out, and S2 also move out. So it will give, due to the presence of lower number of D electron, it will give a shift at the positive direction. So this is a common question, why Fe2 plus gives a positive isomer shift than Fe3 plus. This is due to the presence of shielding effect of D electrons. More D electron mean more shielding effect, and S electron density it decreases, and the shift more towards the positive direction. Okay, this is the answer. So isomer shift is a very important spectral parameter. From the data we obtain from the spectra, using isomer shift, we can find the oxidation state and the spin state of the nucleus, and what kind of bond exactly in the metal to the ligand, and the coordination number, coordination geometry, and to find the very difficult value of S electron density. S electron density can be determined from that, and the parameter, the shielding effect, the effect of shielding effect, everything. This information we can infer from the isomer shift value.